So, moving on to our last lecture in terms of talking about capacitors. And what we want to talk about is how we use capacitors in a circuit. So, as we charge our capacitor, an electric field is produced between our two plates. And the work required for charging that is the work going into creating the electric field. So the energy stored in the capacitor is energy essentially stored in the electric field, and we refer to that as electrostatic field energy. And the capacitance, C, is given by epsilon 0A over D, as we discussed in the previous class, and the energy stored is half CV squared. That makes for a lovely, concise equation if you substitute one into the other, and you'll end up with 1/2 epsilon 0A over D times ED squared will give you this. Usually, what you can do is calculate one and then substitute into the other. But what this will give you essentially is an energy density, how much energy you've got on your plates. So as per capacitors in circuits, what we mean is we take a battery, we hook it up to a capacitor, and then essentially over here we have a bulb. And that will mean this will charge the capacitor before the capacitor provides the energy to the bulb. So energy is being stored in this circuit somewhere else other than the battery itself. So if we're talking about a capacitor in a circuit, what we really want to be able to do is add up how much capacitance we actually have in that circuit. In this particular case, we have two capacitors, a 20 microfarad and a 40 microfarad hooked up to the same battery. Now, the total capacitance here is found by this equation. These are capacitors that are in series. So the electricity comes out of this battery and has to travel through this capacitor and then subsequently through this capacitor. There's only one path for the electricity to travel through, and it must provide the same voltage to the 20 and 40 microfarad capacitor respectively. Now, you're going to see a series of different rules here, one for capacitors and then later on for resistors, and those rules are actually opposite. Now in the case of capacitors, it's inverse in series. That means this is like filling buckets, and these will fill in proportion to how much charge they can hold. That means your capacitors in series are inverse, so that 1 over the total capacitance is 1 over C1, this should say, plus 1 over C2 plus 1 over C3. So in this case, if we're to add our two capacitances, our 20 and 40 microfarad, we have to say 1 over C is 1 over 20 plus 1 over 40. So invert each, add them together, and then invert the answer. If you invert these two and add them together, you will likely get a number that's like 0.4 or 0.6. Not entirely unreasonable, but yet the wrong answer. You would then have to invert that value to get what you needed. And in this case, we're looking at a 13 microfarad capacitor. Now, if we take the same capacitors, the 40 and the 20, and now we put them in what we call a parallel configuration. That means there's parallel paths for the electricity to travel through. So the electricity comes out of this battery and then can split through two directions. Some electricity going through the 20, some going through the 40. And we'll discuss this in terms of resistance later on. But if we look at a parallel system, essentially the total capacitance of this whole circuit is now a little simpler, but not much, the addition of the 40 and the 20 microfarad capacitor. So here, C total is simply 20 plus 40, which will give us 60 microfarads, or 60 times 10 to the minus 6 farads for the whole capacitance. So just like resistors, we can put capacitors into a circuit. And that capacitor can be used to store energy for short periods. And in this little circuit here, there's a number of capacitors which will store energy for use somewhere else in this circuit as it's released. And loads of modern electrical devices have these things: signal generators and processors, power regulation, DC conversion systems, vehicle ignition uses a lot of capacitors, amplifiers, computers, nobody uses DRAM anymore, camera CCDs, the chips that are actually in your camera, in your phone camera that take pictures, electrical weaponry, tasers, lasers, detonators, and radios. So any of these kinds of things will contain some form of capacitor. A camera flash is my typical example. This is actually an RC circuit that we'll discuss. If people remember having a camera flash, you would switch it on and it would make this sound as it charged. So you could actually hear the capacitor charge and the charge build up on it. And then as the pitch built, it eventually slowed down and stopped as the electricity charged that capacitor and left the charge on it to be released in one flash. So if you press the button on this flash, it will release all the energy in one burst. If you were to hook this bulb up to a battery, you would end up with a situation where it would just slowly charge. It would slowly provide charge to the bulb and light it up rather than causing it to flash. So where can you use this? Tasers are a great example. So if you want to tase somebody, what you really want to do is deliver a lot of electrical charge in a very short, shocking burst. And as per this guy being tased, he's about to understand what it means to feel charge running through his body. And tasers, we're only looking at charge of 15 to 500 microcoulombs being delivered. So as I said in the previous slide, not a lot of charge is delivered to actually cause pain, to cause you to be incapacitated. But the impulse duration and the output voltage are the two important things. I think a 10 joule taser would be quite a painful thing to experience. And there's a simple taser. I'll just pick on it because it's a typical example of something releasing energy very quickly. So here's a big capacitor, and you can see this actually only hooked up to a 9-volt battery. So there'll only be 9 volts in here, and you could actually use Q equals CV to figure out how big this capacitor would have to be to deliver a charge that would knock you out. But that's enough about weaponry. We've talked about capacitors, and we've really said that we have this gap in the middle between the two plates, and mostly we've used air or we've used a vacuum between those, in that gap between the plates. You can change the amount of energy, the amount of voltage, the amount of electrical energy that's stored in a capacitor by changing what's in that gap. And that is what a dielectric is. With a dielectric, you're introducing a material that sits in the gap between the plates. And that material will have a unique constant called a dielectric constant. So a dielectric is any material, air, glass, paper, wood, anything that sits between the plates. And that will change how the capacitor stores electricity and how it reacts. And it will have this dielectric constant K that tells you how useful it is at that particular function. So here's what actually happens in terms of the physics. If we have an electric field called E0 that's set up between our plates, if we introduce a dielectric, then the new electric field, which is just E, will end up being E0, the original electric field, divided by K. So if we look at the voltage of our parallel plate capacitor, it was V equals ED. Now E is this E0 over K that we can introduce. Remember, E times D here will wind up being V0 over K. Okay. So we can express the capacitance in terms of this constant. C is Q over V, which is Q over the original voltage over K, so essentially K times Q over V0. Lots of definitions in this section, but usually by context, based on which value you have, it's usually pretty obvious which one to use. I would say C equals QV. In the presence of a dielectric, C equals K, Q, over whatever the original voltage was before the dielectric was introduced. So original capacitance is Q over V0. So for our dielectric filled capacitor, we can say C is equal to K epsilon 0, remember, which was our permittivity of free space. How much electric field was permitted to move through the space between the plates, times the area of the plate divided by the separation. Now, what will happen if you take K and multiply it by E0 is you'll end up with something we can refer to as a new permittivity. This isn't the permittivity of free space anymore. This is the permittivity of whatever material is sitting between the plates, be it wood, glass, plastic, stuffed toys, whatever it is, will have a value of epsilon instead of epsilon 0. So epsilon 0 is called the permittivity of the dielectric, and it's K times the normal permittivity of free space. And that value will depend on K and the unique properties of different materials and how they all react to electric fields. And what this enables you to do is to exploit that factor and tune your capacitor to whatever value you want for capacitance by sticking materials with the right K value in between the plates. So now you don't have to look at the normal equations for C and change E and change D and Q and V as much as you would have done without this particular feature. Now you can say, well, I've got this capacitor, it's a specific size, a specific capacitance, but I want to either increase or decrease it in an engineering sense. And then you can stick a dielectric between the plates to give you the capacitance, C, that you really want. And there's some typical values. So, air is really very close to epsilon 0, very close to the permittivity of free space, and you can see that has a dielectric constant of K. Don't worry about the strength here in kilovolts per millimeter. Let's take a look at this column here. So air, almost 1, very close to permittivity. Bakelite, an old insulating system, 4.9, glass 5.6, blah, blah, blah. Paraffin, oddly, is used quite frequently, 2.1 to 2.5. Polystyrene, porcelain, which is also an electrical insulator. The house I'm living in currently actually has old porcelain insulators down in the basement. They're no longer used, but this house is old enough to actually have very old porcelain insulation. And of course things like transformer oil, which is designed specifically for this purpose. And there's just typical dielectric constants in a more concise table. Water at 80, vacuum at 1. Air, of course, for our purposes, we can compare to vacuum. So what this means for the capacitor is that the energy stored in your standard parallel plate capacitor can be altered by the presence of a dielectric. What we saw before was that Q on the capacitor plates didn't change much when we put the dielectric in, and that was only true if the capacitor was charged and the battery was disconnected before the dielectric was introduced, and questions will often make this very statement for you just to keep things simple. So look for that particular point. But what are we really talking about in terms of quantifiable equations? Well, if we take a dielectric and we insert it while the battery is connected, The battery will supply extra charge to maintain the original potential difference across the plates. And this is why our capacitor winds up storing more energy. So the total charge, Q total on the plates, excuse me, will then become Q is equal to our dielectric constant times the original charge. So for both cases, capacitance, C equals Q over V, is increased by some value of K. So, in terms of the energy that's stored, our dielectric itself will actually lower the electric field inside it and divide it by some value of K. And that gives us our new capacitance, C is Q over V. This is the capacitance equation we saw previously, but now V is the original voltage divided by K. Brings K up here. This becomes K Q over V0, or C equals K times C0. So, just like E0 here, C is affected by K. So your capacitance essentially becomes the original capacitance multiplied by K. This was true, remember, of Q. Q was also the original charge multiplied by K. So if you have some dielectric introduced to your capacitor, you're really just multiplying either the charge or the capacitance by whatever that K number is. So let's take a look at one of these things. So we have a parallel plate capacitor, and it has square plates of a side 10 centimeters, and it's separated by 4 millimeters. We've got a dielectric slab now. That's some dielectric that we're sticking in between the plates with a K equal to 2, probably something like paraffin or something. It has the same area as the plates. What's the capacitance without the dielectric? And B, what's the capacitance if our dielectric completely fills the space between the plates? So what we're saying is that we're going to change the energy stored in our parallel plate capacitor by putting in a dielectric. Here's our plates, 10 centimeters by 10 centimeters, and we're pushing the dielectric of K inside it. So what we have here is part A, the case with no dielectric. Our original capacitance here is going to be epsilon 0 times A over D. This is going to give us 8.85 times 10 to the negative 9 there, farads per meter, times 0.1 squared, divided by 4 millimeters, remember, 0.004 meters. That'll give us an answer of 22.1 times 10 to the minus 9 farads, or 22 nanofarads. Part B stated what's the capacitance once the dielectric fills the space between the plates. In that case, we don't have to recalculate all of this, which is usually the temptation with K slapped in here somewhere. What we can just do is say, well, our new capacitance C is just going to be whatever our K value was multiplied by the original capacitance that we just calculated. So C is going to be K times the original capacitance C0, which is 2, times 22.1 picofarads here, which is going to give us 44.2 picofarads. And there is a larger version of this for you to see. Let's take a look at one more here. Now we have a parallel plate capacitor. Square plates of area 0.0280 meters, square meters, and separation of 0.55 millimeters. The space between the plates is filled with a dielectric constant K. Okay. When the capacitor is connected to a 12-volt battery, it's going to hold a charge of 3.6 times 10 to the minus 8 coulombs. Find the value of the dielectric constant K. Okay. What do we have? Well, from the slide, we have the area 0.028 square meters. We have the separation of 0.55 millimeters. We have a voltage of 12 volts. We have a charge of 3.62 times 10 to the minus 8 coulombs, and we want to find K. So, first things first, what's the capacitance? How do we find that? We have Q, we have V. So this will simply be 3.62 times 10 to the minus 8 divided by 12 volts. That'll give us 3 times 10 to the minus 9 farads. K, well, for K, we can say now C is K epsilon 0 A over D. Why do we use this version? Well, we could now rearrange this for K and say CD over epsilon 0 A. That'll give us, after we substitute in, here's our 3 times 10 to the minus 9, here's our 0.55 times 10 to the minus 3, here's our permittivity of free space, 8.85 times 10 to the minus 12, and here's our area of the plates. That'll give us a nice neat K value of 6.7. So definitely take a look at the last couple of examples, including the one I repeated after I forgot I animated it, and make sure that you can understand what's going on in these two. So I've already said this, the energy stored by our dielectric is essentially 1/2 QV or 1/2 CV squared. And this can get progressively more complicated as you substitute in to these expressions for Q and C. But in the end, what we can say is the energy per unit volume will change based on the introduction of your constant K, your dielectric. And what this means is AD here is the volume of the electric field. So what we're saying is the total amount of energy stored in our capacitor will become 1/2 epsilon E squared, or 1/2 K times epsilon 0 E squared. So a capacitor really stores electrical energy. The electrical energy of the capacitor is this 1/2 QV or 1/2 QV squared, 1/2 CV squared, sorry, which is fine. And energy density is 1/2 epsilon 0 E squared. This definition is used a little less than this one. This is the definition I would definitely make sure you can manipulate. So let's take a look at one example here. So what we've got here is a cardiac defibrillator. And what this defibrillator is going to do is it's going to shock someone deliberately to try and get the heartbeat back into a regular rhythm. And the capacitor, and you can hear these things charge if you listen to a defibrillator with that whistle that I was talking about, the whee that kicks in with something like a camera flash. And the capacitor in this device is charged to 5,000 volts, 5 kilovolts, and stores 12,000 joules of energy. I'm obsessed with 12,000, 1,200 joules of energy. That'll make the blooper reel. What's its capacitance? So, getting it right now, 5 kilovolts, which is 5,000 volts, and it's storing 1,200 joules of energy, which, if you think back to what I said about a taser, is quite a lot of voltage and quite a lot of energy. This is not a fun thing to be zapped with. Don't do it for a thrill. So, how much potential energy U, or PE, is stored? Well, that's 1/2 CV squared. Now, Remember, this is very similar to half mv squared in mechanics, and we often rearrange that to say find a velocity. Very similar, um, very similar idea here, very similar discipline. If we want to find out what c is, this will become twice the potential energy, or 2u, over v squared. Now substitute in, this is 1200 joules, got it right that time, and this is 5000 volts squared. This will give you a capacitor of 9.6 times 10 to the minus 5 farads. So we're nearing the end of our discussion on capacitance here, and one of the last things I want to discuss is what actually happens to the dielectric itself. And in this particular case, we have a dielectric molecule. And what will happen with our dielectric molecule is it will have a positive and a negative side to it. The electrons will be buzzing around a molecule on the outskirts, and the positive charges will be located towards the inside of our atom, inside of our molecule, of course. So the center of the negative and positive charges are essentially the same as, our neutral atom. Apply an electric field, though, and this will actually influence the charges and pull the negatives and the positives off center. And you can think about dielectric molecules as anything where one end of a molecule is very electronegative and the other end not so much. So think back to basic chemistry, and by dielectric, what we're talking about is something like this. This is basically H2O. So this is water here, and this is HCl. This is hydrogen chloride here. Right? So in molecules like this, the centers of the positive and negative charge don't coincide even when you don't put them in an electric field. If you put them in an electric field, they'll be heavily influenced by that electric field and probably experience a movement or a torque. So when we take our non-aligned dielectric molecules and put them in an electric field when they have a permanent electric dipole moment already, what it will do is influence the positive and negative charges and essentially polarize our molecule. And what that will often do is reorient the molecule or move it around so it aligns with the electric field. And this can be useful. So you'll often get a torque exposed to these various molecules. So we stick a material in here that has a dielectric molecule, and then what we can do is essentially switch on the electric field. What that will do is rotate these molecules. The positives will all align towards the negative plate, and the negatives will all align to the positive plate. And you can actually put a physical force onto these molecules. You can apply a torque, or you can shift them through space from one place to another. And it's the polarization of a dielectric in a capacitor that allows you to actually store extra charge in your capacitor. We said when we put a dielectric into a capacitor, somewhere you get extra charge stored. It's not on the plates. Those plates are already full of charge. It's actually stored on the surface of the dielectric. It can't actually be stored inside it. Remember, the electric field inside our conductor is always zero. So the electric field flows around the outside of the dielectric and stores electricity on the outside of it in the form of electrons. So when we talk about a bound charge, it's charge that's bound to the actual dielectric inside the plates. It's actually charge that cannot move from that dielectric as the electric field is set up across it. And sometimes, as you set up an electric field from your dielectric, you can end up with a counter electric field. So think about what's going on with the electric field of these different molecules. Here we've got a positive plate and a negative plate. Now these electrons have all these particles are all aligned, so the electrons are towards the positive plate, and and essentially their positive end, not their protons, but their positive end of the uh, particle is towards the negative plate. And this is setting up an electric field. Here's negative, here's positive for the particles, here's positive, here's negative for the plates. This will actually set up an electric field that's opposite to that of the plates and may actually reduce the overall electric field between the plates. So when you introduce a dielectric which has a polar bond to it, when it actually has a positive negative end to it, a more electronegative end, when it polarizes. Any system that polarizes when you put it into your capacitor plates may wind up reducing the electric field of your plates. And that may be what you want. You may want a smaller capacitance for your device. And there's what the electric field is doing in this particular case. Here is a polarized dielectric. Here's the negative. Here's the positive end of that. Without the dielectric, the electric field is zipping through here, going from the positive to the negative plate. With the dielectric, some of the electric field is held back. And what we can actually define here is how much charge is bound to the dielectric, and that's referred to as sigma B. How much charge is stuck to the surface of our dielectric. And if the dielectric's pretty thin, which we are usually going to assume it is, we will end up with the equation where the electric field EB is now influenced by how much charge is bound, so we end up with the bound charge sigma B on the surface divided by epsilon 0, which is our original permittivity of free space. So yet another definition here, but this only refers to the specific case of the bound charge on a dielectric. And there's that charge. Here we have a sigma. This is the charge per unit area on this plate. Sigma here, charge per unit area on this plate. And here's sigma B, the bound charge per unit area on the dielectric inside the plates. And that's the real difference. And that's what changes our electric field overall. And what does that mean? This means we're once again looking at K. That means E is equal to E0 over K. That's how our electric field will change. And the net field then means the magnitude, the difference between the electric field as it would stand and the bound charge will be E is E0 minus EB, which will give us the original electric field divided by K. Okay, one last word about these polarizing systems, about dielectric molecules, and that is the piezoelectric effect. I believe I pronounced that right. I hear piezoelectric or piezoelectric or whatever, piezoelectric I believe it is. And the piezoelectric effect is one where crystals with actual polar molecules, like the ones we've just been talking about, will actually produce a current when they're put under physical stress. So if we go back here and we actually look at our system here, excuse me, don't often do this, but when we looked at this, we applied an electric field and ended up with a mechanical stress being forced onto our dielectric. The situation we're talking about now is reversing that. We will apply a mechanical stress to our dielectric and get an electric current, an electric field set up, and get an electric current back. And this is what we're talking about if we're being crude. Here's an ammeter, and here is a crystal. Let's whack it with a hammer. And we get a non-zero reading. Now, this is really useful. and it's a little more technical than whacking a crystal with a hammer. I say it's technical, and then I show pictures like this. Um, Piezoelectric crystals will vibrate at very specific frequencies when they are exposed to a current, or they will produce a pulse which is very specific in its timing, and this makes them very useful for things like watches. Go look at a cheap watch. It will all say quartz movement on them. That means there's a piece of quartz there that's subject to vibration. So piezoelectric crystals are used in things like transducers, microphones, anything that senses vibration. You apply a voltage and you induce mechanical strain, or you induce mechanical strain and you get a voltage back. Things like headphone speakers. Flip it around, and things like the accelerometer in your phone. If you flip your iPhone on its side, the screen changes into landscape mode. It is a small device inside there referred to as an accelerometer, which is going to use the strain placed on a crystal to change the voltage, which the phone will then detect and know that it's time to signal a switch in the screen orientation. So this is used in everything, including clocks that you can wear as fashion items if you really want to. So quartz movement, piezoelectric effect is very important and very useful. Just as an aside, there was once an experiment to detect gravitational waves, which we now believe have been detected through other means using much more complicated systems. But the early way of doing this was to take two cylinders about 2 meters long, put them at very long distances away from each other, and see if the cylinder changed shape. The way that was done was to ring those cylinders with piezoelectric crystals and see if two cylinders very far apart on the kilometer wavelength, about the wavelength of gravity, about 10 kilometers or so, to see if they are distorted. If they're distorted, you'll actually get an electrical current produced. And here's one of those big metal cylinders that would be kilometers apart from another. And if one picked up a distortion, one of them produced a current, then the other one should if they got the wavelength of gravity correct. Turns out this particular experiment didn't work too well and gave a lot of false detections. And then getting really classy with it, Batman's cape. Now, if anyone's seen the movie Batman Begins and the subsequent sequels, all of which, in my opinion, diminishing in quality, but then again, people did like The Dark Knight, but I didn't. Moving along. But anyway, Batman's cape in this movie was made out of what was referred to as a shape memory polymer, and people might scoff at this and think this is a ridiculous notion that you could make a cape out of a very floppy piece of material. But in reality, this material does exist. It's not quite as adaptable as the version that's in this movie, but it still does exist. Especially the military in the USA and Britain are working on this very actively, because shape memory polymers are essentially those dielectric molecules we were talking about, dipolar dielectric molecules, and when we put an electric field through them, we can align them, and when we take an electric field off of them, their alignment will be lost. What this means is you can take a floppy tarp that has the right material, made out of the right material that responds to an electric field, hook it up to a battery, and immediately get a rigid structure, as per Batman's cape in the movie. The military application here is to create shelters in a hurry. If you're trying to create evacuation shelters or military tents or things like that, having to carry a whole load of poles and put them together is quite irritating. If you just carry a small battery and you hook it up to this shapeless, folded up cloth, it will then take a rigid structural shape and essentially become a tent in seconds, which can also be folded down by pressing a button. And that's very, very useful. And it's very real. Another place this is also being used, things like haptic displays. And what's that? That's for braille display tablets. People who are blind, people who cannot see, still need to read. And braille tablets, haptic tablets, will actually change their shape. Patterns that can be felt with the fingertips will form on these tablets, and then they will change and they will scroll along based on the electric current that is moving through the surface. So that leads us to the end of our discussion on capacitors. I apologize for the one slide, which was a repeat in there. You can take a look at that in your leisure in the PDF. We will move on next to discussing current in systems of circuits and resistors.